I'm going to go to the final topic that is called photon statistics. So many of you have learned this thing called second order correlation. And second order correlation in the practical measurement, it's come from that. You have photon coming out. Then I have sent it to the beam splitter, okay? And then one detector, if I detect, then I'll start the time counter. The second detector detected, then I'll stop the time counter. Then what I will do is then I'll look at this time. Then I look at statistical distribution of this time bin, right? So what this means, that means is when you detect the first photon, what is the probability of seeing the second photon at time t later if you detect it in there? So then you plot all your distribution, and this is what we call second order correlation function. It is probability to detect a second photon at time t, after detecting the first photon. In the quantum information science language, what this means is when you detect the first photon emitted out, this state collapse, right? Collapse to the ground state, to the vacuum state. Then now you start driving it. Then its probability evolution is completely driven by your control pulse, right? And then if we now measure its probability, then we will be able to see all those time evolution. So if you do think non-resonant excitation, then you will see this famous anti-bunching. The anti-bunching means this is a quantum emitter, so if I detect a photon, then I cannot detect the second photon. I have to wait until this thing goes to the excited state. And its probability is exactly this would be related to its decay time. T1 time is given like that. What happened when you do this thing resonantly? Okay, when we use a very low, weak intensity, indeed, we see the simple anti-bunching. Okay? But now when we start driving it, look, this probability distribution function then acquired this oscillation. Of course, this is, again, famous Rabi oscillation, but no one's seen the famous Rabi oscillation in the second order correlation function for quantum dot. But when we get this result, okay, we've been seeing, this was done using a EG&G, I forgot who, it was Perkin-Elmer detector, has a very long lifetime, time resolution about 300 picosecond. And this, we spent another big chunk of money. By the time correlator, a new APD spent $40,000. Yeah, supposed to have a 50 picosecond time resolution, and this is 300 picosecond time resolution. But for whatever reason, we always never seen this dip go down to 0. Okay, supposedly, if you can see so many Rabi, that means this thing its coherent time is very long. How come we never seen it go down to 0? So that puzzles us. Then I went to a conference, and people told me, oh yeah, those ultra-fast APD, they always advertise to have a very fast time component. But there is another slow time component. They never told you, okay? And that is really responsible for why we see this non-ideal situation. So when I come back from a conference, then I told my students, well, you should see, you should be able to see this, experimentally determine what is the time resolution of this new APD, right? So then we just take a laser pulse, and we look at the time-time correlation, and indeed, we have this very, very sharp line, but unfortunately, it's not like that. It has this very, very long tail component. If you integrate the intensity over there, man, its intensity is comparable to the main band intensity, and that is precisely why it's responsible for that. Now we know what is that instrument response function, then you can deconvolute. We experimentally determine the instrument response function, experimentally determine the data, then the deconvolution is very straightforward. And that is deconvoluted data. And indeed, you can see this is where it corresponds to if you have a very fast time detector, and only that, and you can fit them with a standard, an ideal two-level system very well. And in fact, you can see on this fitting we have T1 time and T2 time. These are not adjustable parameters. These two time scales are experimentally determined on the independent experiment on the same quantum dot. So we determine the T1 using this just time resolve for the luminescence, and we determine the T2 using this resonant fluorescence and look at the bandwidth, look at the line width at a very, very small intensity, and then you get T2 and T1 time determined experimentally, and they fit perfectly well. But I do want to warn you, not every quantum dot fits perfectly well. Most of them fit maybe 70%, 80% well, and then every time you try to present, right? You give people this data, you say, yeah, this is the kind of data we get, but everybody knows you present your best data. Okay, so, and we are no exception, we present our best data on this one, and then you see it fit extremely well, and these are the experimentally determined T1 and T2 time. So you can see this ideal quantum emitter, and then you see that what the Rabi energy splitting as a function of intensity, indeed, everything fit the way it is. But I do want to say one thing, that remember I indicated, say earlier study, we never have a coherently controlled quantum emitter, right? Now I can claim we achieved that. So the reason is, when we say to control this quantum emitter, the goal is to such that the photon carrier will carry the quantum information of your matter qubit. So photon itself is what they call photon qubit, or people call flying qubit. And then the probability of detecting this photon, detecting the photon emitted after you initialize this qubit, its time evolution follow precisely the time evolution of your matter qubit. Okay, and this is why I say then at this point we prove this photon carry this quantum information from the matter qubit. We're going to send it to the other qubit. Now, this is what people call quantum interface, quantum network. But you may feel that I'm trying to say now we achieve that. No, we don't, because we only achieve half. We can transmit from the matter qubit into this photon. We have not yet achieved from this photon, then we get absorbed to the other matter qubit. We can deterministically couple the two. Okay, I will tell you, the first one, even though before we achieved this was considered already extremely hard. Okay, we achieved this now, but the second one, I would say, is probably 10 times harder. Okay, that one is very difficult. And that one requires, because when we did this, the cavity we have is a planar cavity. And there's no cavity QED effect in our planar cavity. In fact, the Purcell effect is expected only about 0.5. Okay, and most of the time we need a Purcell effect about a factor of 10. You know, Purcell factor like a 10, then for us to really harness all this quantum communication purpose. So we have not achieved that. Okay, so then, and that I want to summarize what we have here. Okay, so we now achieved resonant fluorescence for the first time, and pulse excitation demonstrate nearly ideal Rabi flopping, monofluorescence observed for the first time in time domain and frequency domain, and Rabi oscillating second order photon-photon correlation is demonstrated, coherent control of the quantum emitter. Okay, now I'm going to, I didn't do any much about this, how do you do this so-called deterministic generation of single photon, but it's in the presentation, and I think Miss Ogata, is that your, or you have the presentation, right? The PowerPoint presentation, she has it. So if you're interested, you can go and borrow it from this presentation. And you can see this is what I'm talking about, okay? So we have generated this photon. We haven't achieved deterministic couple here. So you we achieved the deterministic coupling here, but we never achieved this yet. And then you, not only that, you want to be able to couple it back. Okay, so that's when we call, if you create a quantum network. And I also have this subject that I call single phonon mediated interlevel coupling. I thought I would have time to do that, but turns out I don't. So I will only list the paper that you can take a look. So in this case, we have demonstrated, first we have demonstrated that you can indeed use, as you excite here, then you can have absorb single phonon and then go to the other state. And we prove it's single phonon, okay? And all the probability follow with all kind of ray equation, we prove that's the case. Not only that, we quantitatively determine what is the coupling coefficient, okay? Then we determine, we can also determine what is this lifetime is. We also determine the excited state lifetime. And so these are what you can determine fit with all the rate equation. Then after you experimentally determine that, then we fit it, then we start looking at the line width of the ground state. So what determines the line width of the ground state is really the T2 time. So this is the way the T2 time evolves as a function of the temperature. And what I plot here with the solid line is assuming all the extra defacing only come from this acoustic phonon scattered with this exciton. And since we know exactly what coupling coefficient is, we determine this kappa coupling coefficient. And we know what population, use Bose-Einstein distribution, we will know what is this phonon population is. Then now we fit, if we assume just all the defacing only come from that channel, what its behavior will be. Then this is the theoretical prediction using that parameter. You can see by the time between 5 to 200 to 20 Kelvin, the whole thing fit very well with just this phonon-induced defacing. But when you go beyond that, well, because now when temperature is high, you have to involve with many, many different levels, then this simple model no longer can account for all those. So I will close and tell you what we have done, and thank you. And don't forget about your homework.